Oh, are we? Yes. Okay. We are. This is 2018 after all. This is the AP Physics C 2012 Mechanics Free Response question number 1. And so let's work through it. And so here's what we've got. And please close the door because that's distracting me, that sound. We've got an experiment here. And we've got a spring constant K. Here's the equilibrium position. And it's got 0.3 kilograms as the mass. And here's our experiment. It says a block of mass 0.3 kilograms is placed on a frictionless table. Ooh, frictionless. I'm going to underline that. When I'm taking the test, I'm going to underline frictionless table, and is attached to one end of a horizontal spring of spring constant K as shown above. The other end of the spring is attached to a fixed wall. Okay, the block is set into oscillatory motion by stretching the spring and releasing the block from rest at time t equals 0. So it's right here when t equals 0, and we're going to release it. The block is, let's see, what does this say? A motion detector is used to record the position of the block as it oscillates. The resulting graph of velocity versus time is shown below. The positive direction for all quantities is to the right. Okay. And so here we go. So then it says A. Determine the equation for velocity as a function of time, including numerical values for all constants. Okay, so now one thing you can do is you can say, well, the position is equal to A cosine omega t. And what we're going to do now is, but we want velocity. So velocity equals A omega sine omega t, right? And this is negative, right? The negative, so the direction of the velocity is going to start off negative. So at t equals 0, the sine of 0 is 0, and our velocity is 0. And then as time goes by, we're going to reach 0 here. Now we need to figure out what A omega is. Well, A omega is our maximum velocity. So A omega equals our maximum velocity. And I can read that off the graph. And let's see here. Looks like it's about there, doesn't it? So that's 0.1. So these are 2, 4, 6, 8, 10. Yeah. So it's 0.246. So it's about 0.16 meters per second. And that's going to be equal to A omega. Now, do they, I don't think they give us the amplitude, do they? So we might use this later. But we are going to have to figure out what omega is. We can do that in just a second. But we know that A omega, that this is 0.16 meters per second. So that's going to be the amplitude of my velocity equation, or the maximum velocity. Just reading it off the graph. Now we need omega. See, these are supposed to be all numbers, and they didn't give us the amplitude, so we need another way of figuring out omega. And so maybe I'm stymied a little bit, but I look through here and I go, okay, well, the period equals 2 pi over omega. Okay, the period equals 2 pi over omega, which means that omega is equal to 2 pi over the period. Okay? And can I figure out what the period is by looking at this graph? Oh, absolutely. See, it's the period is the time it takes for the wave to start repeating itself. So here's right here. So the time from here to here, here's one complete oscillation. So there's the period. And how much time is that? Well, that's just 1, 2, 3, 4, 5, 6, 7. So it's 0.7. So it's going to be 2 pi over 0.7 seconds. So then I get my calculator out. And so I go 2 times pi times 0.7, or times 1. 2 times pi divided by 0.7 equals, and I get 8.98. So now I'm ready to write out the entire expression. My velocity is equal to negative 0.16 meters per second times the sine of omega. Oh, this is in radians per second, or you can just put per seconds, times 8 point, am I on screen? Yeah, okay. 8.98 radians per second times time, and that's my answer. So it's got numerical values for all constants. Okay. Now, now for part B, it says, given that the equilibrium position is at x equals 0, determine the equation for x as a function of time, including numerical values. So now x equals a cosine omega t, and I got omega, but I don't have a, but I kind of started working on this up here. And that'll happen to you as it happened to me, that sometimes you get that. So so a omega equals 0.16 meters per second. So a is equal to 0.16 meters per second divided by omega, but omega is 8.98 radians per second. And look what we get. We get meters per radian. That's kind of what an amplitude is. And so 0.16 divided by 8.98 equals, and I get 1.78 times 10 to the negative 2 meters, or you can just say 1.78 centimeters. So, so I would say that my position as a function of time is my amplitude, 1.78 centimeters, times the cosine of 8.98 radians per second times time. So that's what I got. Let's check the, well, they got 9. They rounded it off more than I'm looking at the solution guide here. So, and they're rounding off more than me. I don't like their answer for x. Ooh, I would ding them a little bit. Look at this. I don't like it when they don't put units in there. But don't worry. I would, even though I rounded off a little bit differently, and I probably should, let's see the values here that they give. They are giving things in terms of 2 significant figures. So I probably should round it off to 2 significant figures. I don't know if they would ding me for that, but I don't know, maybe they would. So this should be 9, and this should be 1.8 centimeters, or 0.018 meters. Okay, now, part, is that right? Oh, it says calculate the value of K. Well, doesn't omega equal, well, equals the square root. I think it's m over k, isn't it? You know, I can't remember. I can't remember if it's m over k or k over m. But here's what I can do. Okay, f equals negative kx, right? So this is ma equals negative kx. So this is a equals negative k over m times x. So this is the second derivative. This is, so it's not m over k, it's k over m. So that's how I remember. Do they have that on? Oh, I'm sorry. Look. They've got it on your equation list right here. 2 pi times the square root of m over k. Well, this is for the period. So if you so the omega is on the bottom. So the omega is the reciprocal of this radical right here. So it's going to be the square root of k over m. All right, so we want to find k, so we're going to square both sides. So k equals omega squared times m. So k equals, and what was omega again? Let's look back here. We'll just go ahead and use their value of 9. 9.0 radians per second. We got to square that. And then what is the mass? The mass was given to be 0.3 kilograms. And so we have 9 squared times 0.3, and I get 24.3. They'll probably round it off to 24 newtons per meter. So K equals 24 newtons per meter. Is that right? Okay. Yay. Okay. Now, for part D, it says the block and spring arrangement is now placed on a rough surface. As shown, the block is placed so that the spring is compressed to distance d and released from rest. Now, this is almost a totally different problem now. Okay? So, now it says on the dots below that represent the block, draw and label the forces, not components, that act on the block when the spring is compressed, a distance x equals d over 2, and the block is moving in the direction indicated. So the block is at, here's d, but here's d over 2, so we're right in the middle here. So now we're in motion, and here we're moving toward the equilibrium position. So the block is right here, we're moving in this direction. So we're going to have the force of friction and then here we've got the force of the spring. I don't know, we'll go F sub F and then F sub S. Now, why am I writing this out? Well, I don't know, just in case they're really, they want us to label the this. And then, of course, a free body diagram, if you're going to have friction, you're going to need a normal force. And you're going to need a weight. or what, and they call it mg. Okay. And then now, if you're moving in the direction, if you're moving away from the equilibrium position, you're moving this way. Well, the spring is still pushing you like this. It's a forced spring, but now the friction is like that. And then, of course, you got your normal force, and you got your weight. Okay. So that, hopefully that was fairly straightforward for you. By the way, I'm going to finish this, so if the bell rings, you guys can just go if I'm not finished with this. But now this one, I peeked ahead, and when I was reading this, I go, wait a minute. It's the same mass, the same spring, so it's going to have the same period. So it's going to look like this, and let's see, about 0.7, and then you have 0.35 like this. But the velocity is going to start at 0, and it's going to come up to some maximum, and then it's going to come here. But because friction is taking away the energy, the amplitude is, the amplitude is going to get less and less until it stops moving. Now, originally I thought, oh, they're going to want to know how many amplitude, but this I think this is as far as they wanted you to go. Anyway, does that make sense to you guys? The amplitude's getting less and less because it's taking the mechanical energy away. I was thinking we were going to have to figure out how much, but evidently not. That is